Hello, we're Group 12, and this is our independent group project. We studied the college scorecard dataset, and we looked over the 2014 to 2015 school year. We dropped all the NA values, and we ended up with 993 observations. So for my research question, I asked, are SAT scores alone sufficient to explain variability in 10-year post-collegiate earnings, or do ACT scores provide significant additional predictive power? So these are my variables: average SAT, 75th percentile ACT, 75th percentile verbal SAT, and 75th percentile math SAT. So these are the graphs for the X variables. You can see that they all have a positive linear relationship with the Y, as well as they all have high outliers. So for the original GLT test, we have the reduced model without the ACT, and then the second model is the full model with the ACT. So this full model was statistically significant, so it suggests that ACT scores do provide statistically significant predictive value. So our initial MLR model includes all four variables, including the ACT. So here are the coefficients. And for the significant, all of them have low p-values, so they do seem to be significant, as well as the model itself is significant. For the coefficient of determination, we have the predictors explain 45.68% of the variance in the median 10-year earnings. For the VIF, we have that two of our variables are over 10 and two of them are over 5, so this shows a lot of multicollinearity, so we might need to reduce, so we will need to reduce this. So for the linearity assumption, this was violated because there is curvature in the residuals plot. So this deeper dive into linearity, I looked at the residual plots for each independent predictor, and they all have this similar curved pattern, so I can want to square these predictors. For the constant variance, this is also violated. Our Bruch-Pagan test value is pretty low, so there is heteroscedasticity present. For normality of errors, the line does stray from the QQ does stray from the line, so this is also violated. We will need to keep an eye on this assumption. For the outliers, I took out all of the outliers that are over these thresholds, and I ended up removing 44 outliers. So fixing linearity. To fix linearity, I squared all of the predictors, and as you can see here, this residual plot is much nicer in terms of randomness. Fixing heteroscedasticity, I logged the Y variable, so this Bruch-Pagan p-value shows that it was a lot higher, so the residuals are roughly randomly spread. For reducing predictors, I looked at the adjusted R-squared, the CP, and the BIC, and all of these showed that at 5 variables, these were the best. So I chose the model with 5 predictors, and these 5 predictors are here. For multicollinearity, we can see that all of these are now less than 5, so multicollinearity is no longer an issue. For the final model, we have the log of the Y variable with the SAT average squared plus the SAT verbal 75th percentile squared plus the SAT math 75th percentile. And here is the interpretation of each coefficient. And here is the significance. So they all have very low p-values, so they do seem to significantly affect the log median 10-year earnings, and the model itself is also significant. For the coefficient of determination, this model increased it by about 0.6, so the predictors explain 51.38% of, 0.06, sorry. So the predictions explain 51.38% of the variance in log median 10-year earnings. So we improved the linearity with this final model. We also improved the homoscedasticity, and we improved the normality of residuals. There are still some outliers here because I was a little bit lenient with the cutoffs, but I was worried about losing too much data. So for the conclusion, the initial partial F test showed that ACT scores are significant. However, after transforming, the ACT score variable was removed. So any effect of ACT scores on the post-collegiate earnings was not robust once the model assumptions were addressed. So this final model does satisfy the regression assumptions, and we can reliably interpret and predict using the final model.
Hello, this is Suyun, and I'll give you a talk about my research question. In this study, we used US scorecard dataset to examine the relationship between tuition pricing and undergraduate enrollment. We focus on two main research questions. First, does tuition differ across different household income groups? And second, does tuition from these income tiers influence the number of undergraduates enrolled at institutions? Tuition is divided into 5 tiers based on family income, and number of student enrollment is our response variable. To test whether tuition differs across income groups, we ran a one-way ANOVA. The null hypothesis is that all 5 mean tuition values are equal, and the F-test was extremely large with a p-value near 0. This tells us that tuition levels do differ statistically across income tiers. The box plot reinforces this, where tuition amount increases consistently as family income rises, with lower income students receiving more aid and higher income families paying closer to full price. Overall, the institutions clearly differentiate tuition by income group. For our second research question, we examine whether tuition from these 5 tiers predicts undergraduate enrollment, and our analysis follows this flow chart. We start with a flow model with 5 predictors, where Y is enrollment and X1 to X5 is tuition levels for each income tier. The initial model showed extreme outliers with strong leverage points and large Cook's distances, and after removing these observations, we refitted the model, where the adjusted R-squared improved from about 0.16 to 0.22, indicating that the outlier removal meaningfully strengthened the model. Next, we examined added variable and component plus residual plots, and the patterns showed that low-income tiers have a weak negative effect on enrollment, and mid to upper tiers have a clear positive partial effect, and the highest tier has a flat or unstable slope, suggesting strong multicollinearity. This supports the needs to reduce and reorganize the predictors. And we attempted several ways to collapse the tiers. A simple low versus high, which is a 2-tier model, performed poorly, and it even reduced the adjusted R-squared. So then we used ESS or GLT tests to compare restricted versus full models. We grouped the coefficients in different combinations, and most combination failed statistically, but one grouping passed, which was when beta 1 equaled beta 2 and beta 3 equaled beta 4 and beta 5 was separate. This leads to three meaningful groups where beta 1 and beta 2 can be classified as low income, beta 3, beta 4 as mid income, and beta 5 as high income. We then refit the model using these 3 predictors, and this produced clearer linear trends and smaller standard errors while maintaining adjusted R-squared around 0.21. However, diagnostics showed heteroscedasticity with a funnel-shaped residual pattern and a significant Bruch-Pagan test. To address this, we log transformed the response and ran weighted least squared methods, and residual spread improved visually, although adjusted R-squared decreased slightly to about 0.19. And the Bruch-Pagan values still remain large because of the large sample size. However, QQ plots and residual plots show that the model improves. T-based and bootstrap confidence intervals remain consistent for low-income tiers, indicating model reliability. Mid-income effects remain positive with intervals slightly widening, and high-income effects stayed weak and small. And so overall, WLS assumptions adequately model the heteroscedasticity, and the T-based intervals are reliable. Even after collapsing tiers, multicollinearity persisted. The mid and high income predictors had a high correlation around 0.93 and VIF values above 10. First, we thought about collapsing all tiers, meaning that all income tiers doesn't influence student enrollment. Rather, the tuition itself is the only predictor that matters. However, this has a very small adjusted R-squared value, which produces non-meaningful results. And this required further mitigation using 2 complementary approaches, either using ridge or orthogonalization. So we applied ridge to the transform model of log y because it solved heteroscedasticity, and ridge regression stabilized coefficients for prediction, but the shrunken coefficients are not directly interpretable. We ran a small example using ridge by obtaining the average tuition fees for each tiers, and then we were able to estimate around 2,957 students would be enrolled at the average level. Now, for interpretation, we used orthogonalization, isolating each predictor's unique contribution. After orthogonalizing the mid-income tier, all 3 coefficients became statistically significant, and multicollinearity dropped sharply, and VIF values fell below 5. The high-income tier now shows slightly positive impact, indicating more students would enroll even with higher tuition. Lastly, putting all the results together, we conclude that overall that tuition influences enrollment, but the relationship differs meaningfully by income tier. Low-income households, tuition brings a negative effect, where higher tuition leads to fewer students to enroll. For mid-income households, tuition has a positive effect, where higher tuition corresponds to more students enrolling, and high-income tuition has a weak or inconsistent effect, likely because the households are less price sensitive. So that was all for my research question. Thank you.
Hello, my name is Philip Goldberg, and this is my research question. My research question is, what impact does the added cost of going to college out of state have on college completion rate? In order to analyze if out-of-state tuition cost has any effect on completion rate, a general linear F-test is completed with a reduced model not containing out-of-state tuition and a full model containing all of the necessary predictors. Looking at my hypothesis, the null hypothesis is the beta cost tuition out will equal 0, meaning the reduced model is sufficient and cost tuition out will have no effect on completion rate. The alternative hypothesis suggests that the full model is significantly better and there is an important impact for cost tuition out, and the variables are defined as shown in the slide. Looking at some dataset variability, the initial Cooling dataset contains 993 observations, but 3 observations in that set contained a 0 for completion rate, so these were removed from my analysis, making a number of observations of 990. Looking at some initial descriptive statistics, an important thing to point out is tuition in-state and out-of-state have very similar fourth quartiles due to private schools having the same in-state and out-of-state tuition, and the standard deviation and variance can be seen for the variables. Looking at the general SLR model, an interesting phenomenon is that generally more expensive schools have higher completion rates of in-state tuition, out-of-state tuition, room cost on campus, and room cost off campus, all having a positive correlation to completion rate. This could be due to the fact that normally higher completion rate schools could generally be more expensive and be better performing and just get better students that get through college. But moving on to the MLR model, the room and board off campus becomes negative. This could be due to the fact that off-campus housing as well as books are generally not as school dependent and they're more area dependent of where the school is located. Moving on to the GLT test, with a 95% confidence with these general predictors and data points, we find a critical F value of 3.851. While there's a test statistic of 216, suggesting that the null hypothesis should be rejected and the full model is significantly better, making out-of-state tuition costs have an impact. Looking at some assumption checking for linearity, there is minimal curvature in the residual plot, and while the added variable plot suggests much of the impact is just from out-of-state tuition, it's reasonable to assume linearity, and to this point, we're going to keep all variables. Moving on to heteroscedasticity, there's the Bush-Pagan test, which suggests a lack of constant variance, while the Brown-Forsyth test does suggest constant variance. This difference can be due to outliers, as the Bush-Pagan test is very sensitive to outliers. Moving on to normality, the Shapiro-Wilk test suggests a lack of normality, but the histogram appears fairly normal, about 0, and the QQ plot shows a fairly strong linearity besides the tails at the end, which again could suggest outliers in play. And with outliers, looking at a leverage of 3p over n, a student has residual above 2 for a 95% confidence interval, and a Cook's distance above 0.5. There are 72 defined outliers in this data set. A closer look at the top outliers, which are outliers in both the x and y direction, we suggest, for example, the University of Florida having a leverage of about 0.038, and a student has residual about 2.51, meaning it observes a higher prediction, or observes higher than the model predicts. With a high completion rate, the 84th highest, with low tuition cost, high books cost, and high room and board off campus costs, it suggests that the completion rate should actually be much lower than University of Florida has. A similar case is seen for William Carey University as well as Penn State University. But for Long Island University, the opposite is the case, with a student has residual of negative 2.05. With a 22.32% completion rate, that puts it heavily in the first quartile and not that great. But it has the highest room and board off campus cost and the fourth quartile for in-state and out-of-state tuition costs due to it being a private school. And it also has a very high room and board off campus cost, meaning that realistically the completion rate should be higher for this case. There are also other outliers in just the x direction and y direction that are seen in the slide based on completion rates to their defined variables. Looking at the correlation matrix, there's a noticeable correlation between cost tuition in and cost tuition out, and a concerning multicollinearity for cost tuition out, which is most likely due to private schools again having same tuition in and out. But when you remove private schools, it solves the collinearity but leads to many assumption violations, and it is good to move forward for this model as the multicollinearity isn't too bad, with private schools still being included. After removing outliers, there is a notable increase in the R-squared value, moving from a 0.572 to 0.685, meaning 68.5% of the error is predicted by this model. And looking at the ridge regression, the lambda min is very close to 0, suggesting the OLS model provides a reasonable fit. And all of the confidence intervals not including 0 means that all the variables are significant in this case. Moving on to AIC and BIC for a non-nested model, these being low suggest a well-fit model, and it being negative also represents a good model, and removing outliers did lower both of these values. So in conclusion, overall, a higher out-of-state tuition cost has a positive effect on completion rate, and the original model is predicted as sufficient.
Greetings, my name is Caleb. I'm going to present my part of I'm going to present my research question of this group project. In this case, my research question is that we're going to look at whether or not the cost of in-state tuition and out-of-state tuition affect the number of enrollment of undergrads for colleges essentially. So we're going to look at our variables. We're going to look at okay. So you can see like our variables. Our y variable will be the number of undergrads. Everything else will be our x variables. As you can see, and then going onward, we're going to look at our initial MLR model. We see that almost all of the variables, except for cost of books, is statistically significant, and the model itself is statistically significant after we look at the p-values in this case. Moving onward, we're going to check the assumptions, see whether or not the OLS model, as shown before, holds or best represents the data. So in this case, for the assumption of multicollinearity, there is some multicollinearity using general rule of thumb for the cost of tuition for out-of-state. However, the difference between 5 and the value for cost of in-state tuition, out-of-state tuition, isn't that big. So there is some moderate multicollinearity, but not a huge concern in this case. Going on to the assumption of linearity, we can see there's a violation in this case. As you can see, look at the overall linear regression. There is some curvature in this case. Going forward, we look at the partial regression plots for all the x variables, and we see that there is some curvature for all the x variables in this case. So that means we have to transform x. Then looking at the Prush-Pagan test for constant variance, we could then see like, hey, there is a violation here based on the p-value. And then going on for the normality of errors, Shapiro-Wilks test, we can see there's also, a violation to the assumption of normality of errors in this case. And due to the QQ plot shape, we may also have to transform y or take the log of y and do the WLS in this case. And then going forward, we could then look at the outliers and we could see, some extreme outliers like case 738. And looking at the Cook's distance at the rightmost graph, we may also have to apply the robust regression as well to, this model really. And then to this data to be more precise. Going forward, we clean the data, as you can see how many we cleaned from and what sort of number of data after cleaning. And afterwards, we took the robust regression. I did Huber and Tukey, and just to compare the results, we can see that about half of the variables here and their components are statistically significant. However, what is noted is that the cost of tuition for in-state and the linear component for the cost of tuition for out-of-state is statistically significant based on the t-stat variable and all that, which is important because we're looking at whether or not the tuition affects the number of enrollment for undergrads. There's also bootstrapping here. After this, we're going to check whether or not the assumptions has been violated or not. But for multicollinearity, there's no, value above 5 on the right-hand column. So in this case, there's no issue with multicollinearity. For constant variance, using the Prush-Pagan test on the WLS and comparing the residual versus fitted graph for doing Huber, Tukey, and WLS, we can then say that, in this case, constant variance assumption isn't violated. Then going on to the normality of errors, we can see that from before, compared to before, normality of errors has greatly improved. However, due to the amount of data on this QQ plot right here, we can't say entirely for sure that normality of errors isn't violated. So in this case, it's at no amount of errors assumption has approved, but wasn't but isn't, but it's like still violated in some cases maybe. Moving on, we look at linear assumption of linearity and looking at the overall linearity, we could say that hey, has greatly improved and possibly not violated in this case. And so in conclusion from the WLS and robust regressions, we can say that all the assumptions have been improved upon or aren't violated in this case. And then in conclusion from based on the regressions, tuition for out and in of state does have an impact on the number of enrollment for undergrads in this case.
Hello, my name is Avery Fry, and this is my research question. So my research question was if college selectiveness significantly affects the average cost of attendance for when we control for public and private institutions. We're going to use a GLT test with a reduced model that is only based on if it's a public or private institution, and a full model that includes some of these selectiveness measures. And we're going to compare the two to see if we find a significant difference in the prediction for average cost when we use these selectiveness. So we're just looking for any kind of impact selectiveness has on average cost. So these are the variables we're going to use. It's going to be the average total cost of attendance, the admissions rate, which is a percentage, some test scores, so ACT, SAT, both math and verbal, and also the control, which is if it's a public or a private university, to help us control for if it's a public school or a private school, just because we knew going into it that private schools have a significantly higher cost than public schools. So we made an initial MLR model. We can see here like admissions rate, SAT verbal and SAT math were significant at the 0.05 level for private schools. None of the difference between private and public were significant. But we do see here that they did have some effect. So it seems to be that perhaps selectiveness does have an impact on average cost. And that's confirmed with our initial GLT-F test. So we see here that we get an F value of 33.6 and a very, very small P value. So this kind of initially suggests to us that perhaps we want to reject our null hypothesis, but we first need to check our assumptions. So getting into assumption checking, we see here that our residuals seem to be fairly normally distributed, no real patterns here. We see a little bit of clustering, but after checking, this was a public school cluster and a private school cluster. So kind of makes sense. And within the groups, there's no real craziness going on. Our Q to Q plot looks pretty good. We see we have some problems at the tails, but not too bad and not enough to really warrant huge remediation with it, especially controlling the way we are. This is a very controlled experiment. But we do see that observation 985 and observation 115, we did end up removing these. They just have such high standardized residuals and leverage, and we see them here on our influence plot sticking out. So we did remove these two values when we were moving forward with the rest of our analysis. We also want to check multicollinearity, and this is where problems started to arise. So we see we have severe multicollinearity issues for all of our test scores, and we want to we're going to have to do something about these because it's going to make our confidence intervals explode. So we did ridge regression. We identified that these three were pretty similar, but we didn't want to just combine all of them because ACT and SAT scores on separate scales. So we decided only to combine the two SAT scores and see what that did. And we can kind of call that a new like 25th percentile SAT total. Throwing that in here, we see now we have much stronger relationships with admissions rate, SAT total, and a significant difference between public and private schools, as shown down here with our SAT total score. So this just looks like a much stronger model, and our adjusted R squared is the same, so we didn't lose a whole lot of performance. And now we can check multicollinearity again, and we see this is much better, 1.7 and 1.6. There's no concerns here about multicollinearity. We're not even in the warning zone. And then when we run our final GLT-F test, we see here an F score of 66.2. This made our result even stronger. We reject our null hypothesis, conclude that school selectiveness does have an effect on admissions, on average cost. And we see here that admissions rate actually has a positive impact, which if we were trying to explain that, we might want to dive into deeper. But here we just conclude that we reject our null hypothesis. So yeah, we've seen multiple different research questions answered here today. Every single time we attacked it, we checked our assumptions, and we drew some interesting conclusions. Thank you.